Hello, I'm so sorry for starting this late. Since I do see that there no one has joined yet, I'll like wait for 10 minutes. I'll just get my time to wrap things, like set things up, and then we'll start the session. Okay, please bear with me for today. So this is a week 3, and I'm Jagriti. Today we'll discuss about logarithms at first because it wasn't told to you at last, and then we'll go through general rules of differentiation, first and second order of differentiation, and then later the previous year assignments. So um, we'll just start like approx. Now it's 6:12. We'll start from 6:20. I'll do my setup. I'm a bit delayed today, so we'll start at 6:20. Okay. Okay, so thank you for bearing me till now. So I promise this won't happen in next time. So yes, starting off today. So in today's class, we have curvatures, what different curves mean, first and second order derivatives of the same, and then we have L Hospital's rule, and then we conclude the week by solving the last year's assignment. Okay. So till now we have last week we saw different applications of we first started off with trigonometric identities, and for that I have removed those slides over here. But yeah, you all know that this is the book that you'll have to refer for this particular course going ahead. And then, since on the very first week, the expansion for all different series were directly given to you, so we didn't know the exact root of it or from how to derive this one particular equation or expansion for, let's say, sin x, e raised to x, log x, and all from cos x and all different trigonometric identities. So for the same, there are like this Taylor series generalized expansion formula, which is like stands on and derivatives, which are like nth derivatives, and then this particular series, when evaluated at zero, it turns to Maclaurin series. Okay. Now, uh, post it, we saw how to, sorry, I'll just present this one slide. Yeah. After that, we saw that how can we derive e raised to x, or let's say sin x or cos x, and all these different terms for it. But at that particular point, you all weren't aware for log x or ln x. And for others, we saw the equations and formulas for and graphs also. However, we have not yet touched upon this inverse trigonometric functions that will do as and how it's needed. So then we saw that, okay, how's the internal rule of derivative? And from graphs, we also saw that how do you evaluate a derivative at? So what do you do is like you evaluate the derivative or the slope of a function at two different points such that the delta x range approaches nearly to zero. It's a very narrow range where dx approaches zero, as it's written over here. So it's like limit where dx tends to zero. That so over here this limit is being applied so that your denominator term makes your function as small as possible, so that you get the slope as a very accurate slope in between those 2 points. The first, let's say a1 and e2 point that you want to take. Okay, so you choose an interval, so two such points, let's say x1 and x2, and you define the range in between them, that's delta x. You find the raw change, then you find the rate at which it is being changed, and then you make that delta x to as approaching zero. So make your model perfect. Okay. So post it, we saw this simple functions where it's like, okay, if I have a increasing parabolic function, so this is like increasing one, where it's like the first slope tends to decrease, the blue arrow, whereas the red one increases. Similarly, if you see over here, the second one, the downside shifting parabola, this side it's increasing, then later it's decreasing. Now, when we take the derivatives, we see that, okay, this one is decreasing, but at first it had a constant value and then it's decreasing. It nothing but it's crossing zero. After a certain value, it is again increasing, crossing zero. So we know that, okay, after a point, now this is decreasing, then it's constant at these two rates. So it's constant over here, then it's crossing zero, and then it's again increasing. So this is the slope that we get from here. The final crust of this is that this is eventually an increasing slope. Okay, so your slope is positive and that nature. Similarly, in this particular context, you see that uh, for the first one, you see over here that this is increasing. Again, this over here is decreasing. So you see in this particular case that your entire slope is nothing but decreasing. Initially, you had a one positive value, then later the slope started to decrease. So from there, you can get an idea that, okay, how different slopes change. If it's a convex or a concave, you get an idea that whether it will increase or decrease. And then from there, you can also get an approximation of how its derivative function will look like, even if you don't know how derivatives work. Okay, and then later we also saw the formula for derivative to compute a derivative of a function. So that, of course, you can do at this particular stage. So for sin x and cos x, we just took two different examples and we evaluated them as that, okay, if sin x is over here, it's increasing, then it's later decreasing. It's starting from zero and now it's increasing. So till this particular point, it had a constant slope, increasing slope. So we know that, okay, for sure, cos x will start from a constant value. Now then, hence by it's decreasing over here. So later while it will follow the similar trend. So from here, if you want to go like one step, so if you want to go like backwards, how you can start is like now you start evaluating the limits from this particular point of cos x till this, because we know that the limits for sin x are like the range for x how the for sorry not for x but for y the range goes from 0 to 1, whereas for cos x it's nothing sorry that is from negative 1 to 1, and whereas for this particular case it's from 0 to 1. So when going from this way onwards you'll get this first slope and then later, so it's nothing but it's shifted by pi by 2 if you talk in terms of degrees or radians. Okay. Similarly, for this, if you have a positive slope, you'll have a constant value. Later, it's decreasing. So again, a decreasing, a constant in the decreasing side, again increasing and decreasing. Okay. So the whole message of all these things were that you try and make your this delta x limit as small as possible so that you get the rate of change of f as that particular in between those two intervals that you have. So in this case, it's x plus delta x and the other one is x. So your range is nothing but delta x. So you have this delta f and you have a delta x over here. Okay. So with that, this is like a generalized definition of how do you compute a slope or how do you compute a derivative. You just, so here h in this term stands for our dx, but just in case like we have written this in a formula of dy by dx, that's why we are not using the same terminology here. In a way, it's nothing but just using different variables to present the same thing. So you get that, okay, you have it. And so in this particular case, our limit, our range of interval is this h. So we are evaluating our limit at that particular h. Now, if it had to be then at a, then it would have been x minus a. So if your x tends to a, that eventually means that your x minus a is nothing but 0 and it tends to 0. Okay. So that's all for derivatives in this particular case, and you already know the rules for it. So I hope till now, if you have practiced enough, you will get an hang of it. If not, then you'll eventually, as in how you solve multiple examples, don't worry that this is not only about solving different examples about it. It's just that you need to understand how, if something comes up, if you get a equation to solve, like, okay, if someone has given you some quotient and products and some powers combined all together, you should not be surprised or shocked that, okay, how I'll solve that. There are like simple rules for it. If it's a constant, it would be 0. If it's combined with a function or with the variable that you are evaluating the derivative with, it would be just the constant value. If it's a two different independent variables, then you can just separate them out. It follows the principle of additivity. Then if again a subtraction, it also follows the similar thing. There are two special rules here. One is product and one other in is quotient rule. So in product case, you take the first one constant, do the derivative of second one, then keep the second one constant and do the derivative of the first one. Okay. Now, in case of your quotient rule, you can again follow the same thing. Now, only change is here that instead of doing, let's say here you had u times v in the first case, here you have u times 1 by v. Okay. So you follow the same product rule, you'll get the same answer in that particular case. Or in case if you don't want to, or like because the product rule formula is like simple and you don't need to remember many things in that case. Whereas the quotient rule does has, but it's also simple. Like you do the derivative of the numerator at first, keep the denominator constant, subtract it because it was in the denominator. It had a sign of -1, right? Because when you write u times v raised to -1, that is nothing but u by v. So here it is u times, so you have this minus sign for that case. And then for and how it was derived from this product rule, it had a denominator of v square in this particular case. So you can always derive the formula of quotient rule from this product rule. And then you have chain rule. What chain rule means that if you have a function and then that function is also dependent on the function that you are evaluating your derivative with. Right. What that means is if you have u raised to a, then what you'll do is like you have a minus 1. That's your simple power rule. But now this u is dependent on x. So how it's written over here is also wrong in a way because this had to be written as u of x raised to a. So in that case, you'll understand that how is it dependent on x. So here it is u of x. U is a function of x. So we'll again differentiate u with respect to x. Okay. So I hope till now all the differentiation rules and formulas are clear to you. If yes, then I'll go with today's class. So last time when I was solving this assignment, we all came upon few things that, okay, we saw that, okay, I hope my screen is visible. Let me check if it's visible first. Yes, it is. Okay. So we saw that there was one question on log, and it was not yet clear that from where does this log come from and how do you solve for log. But it's fine. Like you might have seen it till your class 10th and 12th assignments. But if not, then I'll just quickly go through some simple basics that you should know for solving logs. But that will take on the end of this particular class. For first 30 minutes, we'll cover up the lecture content that we have for today. So we have like starting off from, I guess we have couple of lectures today. That's lecture 11 to lecture 15. So the first one is like curvature and second derivatives that we just saw now, that how curves change and the slope of the curves also change. So we'll just take that first, and after following till L hospitals rule. So that like people call this L hospitals as L optiples also, or L optals as a, like it's like that L optals. So there are different pronunciations for it, but if you just go by what it's written, it's L hospitals too. So I call it as L hospitals. Yeah, okay. So we'll look at that also, and then follow that we'll do the last week assignment, and then later if you want to, I'll solve for the log. As like I'll just show on that, okay, what are few basics of logs and what you should know. Also, I'll skip one particular lecture in this particular week that I already covered in slides just now. That was about Taylor series and expansions. So I don't know how it went, but somehow probably prof had wanted to show you about the expansions of sines and cosecs previously, and that's why it came popped up in week one. Well, it should not have been, but it's fine. So now you know about Taylor series and how to solve for a function, so you can evaluate any particular function when given to you with the formula that we have already read on. If not yet, then you can always go back to last week's assignment. We had like I had solved for a few examples like e raised to x and then sin x, so you can always go through it. If not, next lecture you can ask me and we can solve one more assignment, one more example for it if you want to. Okay. So with that, we'll start for this week. Sorry. Yeah. So for this week, we have, it's not working. I hope it's visible what I'm writing. Right? Yes. So we have curvature and second derivative. Okay. So I won't write many things. I'll just show you through graphs only. Right. So let's say we have this one particular curve. There are no students yet today. So I was meaning a interactive session today, but it's fine. We can always go back to the YouTube slides and have a look there. The sessions are made public to you for you to see. Okay, so if you have this thing, and then so this is nothing but it's showing that it is increasing, right? So at this particular point, it's increasing. Then in between these points, I see that it's constant. And then similarly for this particular points, it is like decreasing again, right? So what do you see? In this points, it has a positive slope. So I'm representing M as slope. This we had a constant slope. So a constant slope means nothing but dy by dx is equals to 0. So that means m is equals to 0. So have this as y and then this as x. And then we have this as a negative slope in this particular case, which means dy by dx is nothing but negative. And then this particular case, dy by dx was what? It was positive. We already saw that how do you plot a derivative for this. Now which type of function is this? You see it as a convex function, right? So this is a convex function. The opposite of it would be a concave one. So that I'll leave up to you guys for you to see. So okay, now what do we see over here? What we see here is the slope decreases as we go along x, right? So as in how we go along x, the value of m decreases. The slope is nothing but decreasing. What that means is that your dy by dx is nothing but it is decreasing, right? So you have that one particular term. Now, this is your slope that's being decreasing, and that's nothing but m. But what now we are looking at is nothing but how the nature of your slope is changing, right? What you're looking at is the nature of slope. That is nothing but your curvature, right? This nature of curve, how it's being changed. That curvature is being told to us by change in slope, right? So what is change in slope now? Change in slope would nothing but dm by dx. It would be represented as this, which is nothing but d by dx of dy by dx. Okay, so till this particular point, it's clear. Now, how do you write it as? Now, this is nothing but double differentiation. You have this first derivative, you have the second derivative. So, how do? You do d square by d square y by dx square. You write it like this. Okay, so this is, it does not mean as it, this is not at all equal to dy by dx whole square. Okay, never ever do this one particular thing that you'll find the derivative and then you square it up. It's totally different from this one particular point. Okay, so that's d square y by dx square. It's like being pronounced in the same way how it's written. Okay, so how in this particular case we say that the slope is nothing but decreasing, right? So the opposite of this would hold true for which particular case? For the concave case, right? In that case, your curve would something be like, and for this one, it would be like this, right? It is decreasing here, then it's constant here, and then it's increasing here. So in this one particular case, you see that, sorry for the disturbance. We in this case we see that dm by dx is positive, right? The nature of the slope is nothing but increasing for this concave case. So you know that your d by dx of, I'm writing this again and again so that you can see how it's being written and you just don't memorize it. So we see that this one particular quantity is positive in this case, whereas it was nothing but negative in this particular case. Okay, so now if this is clear, we'll just give one example. So let's say if I have a curve, something like this. Okay. Oh, sorry. Ah, that's nice. Okay. So let's say if we have something like this and let's have some contrast here. We have a contrast. Yeah. Let's take yellow. It's more contrasting. Okay. So if we have something this, now what do we see over here? We see that this is what? It's a maxima, right? Something that's increasing. What is this? It's a minima where it's decreasing. Then what is this? It's again a maxima. It's increasing. Now what do we see over here? It's an increasing slope. Nature of slope is increasing. Here it's constant. Here it's decreasing. Here it's increasing. Again it's constant. Sorry, it was constant here also. And then it's decreasing here. Right. Now how do you mark it as? Now what do we do? In this particular case, we see that dm by dx is positive. Right. Now, this is one such example of a curve where you have both minima and maxima both together, all together with you. Now, this is a case where dm by dx is 0, your slope is 0. This is again a case where it is nothing but negative. This is 0, this is positive, right? Sorry. Maximum. In this particular case, it was positive. This is 0, and then this is negative, right? What is 0 and negative? That's dm by dx only, okay? Hence the same color there. So we see that the curvature is increasing and decreasing, and the filaments, and the filaments, what? And the curvature keeps on changing over here, hence your slope is also changing. So you get curves like this in a way, and then there are some examples, not examples, practical cases in biology, where in case you need to whenever, let's say, you're making a protein, or you're not a protein, a peptide synthesis, you're trying to do DNA synthesis, you're trying to see strands of DNAs, how they are looping around, how they're bending around, and you're trying to do some mass spec analysis. In those particular cases, you're trying to see how much stress or tensile stress a particular molecule has. So in those cases, whenever you're trying to evaluate the energy of that molecule, how much energy it needs to bend or stress on, in in that particular scenario, this case is where, okay, it is being increased by this much nature, the nature is increasing, the nature is decreasing, will help you evaluate how your one particular structure is going through. So there are examples like, okay, for one such as DNA, people look at chromatin, how the structure of chromatin is being changed, they evaluate the energy of it. So people do things like that, and in their experimental setup. I'm not aware into most of it, but I do know that how instruments this work, and this is the maths which is behind it. This simple maths is like it. So you see over here that what it tells you. Now we have seen that mostly everything that we have seen is this dm by dx, which tells us about the curvature, right? This quantity will tell us about the curvature, the change in curvature, whether that change in curvature is positive or negative, or whether the change in curvature is small or large, right? Whether that change is small and large. And what do we see in that particular case? That it was d square f by dx square, and that is equals to our dm by dx, and that is equals to this one constant slope that you have, the curvature that you have. Okay. After that, you have something as plotting curves. I won't go into more of it, but I'll just show you. Now, how do you notice that now we use terms like maximum, we use minimum, again we saw maximum. Now, what do we saw? When it was constant, the slope was constant in the cases where it was maximum and minimum. So what do we know? That whenever you have a maxima in your slope, in your curve, or a minima, the value when it tends to zero, you first need to evaluate your derivative at zero. So at this particular cases, it would be at zero, right? So first thing that you have to do is you do this. Now, when you do this thing, after looking at the sign of it, if it's positive or negative, you get to know that if it's maxima or if it's a minima. Okay, it's always a positive way. If it's positive, then it's a minima. If it's negative, then that's a maxima. How so? Because the slope is changing. The nature is being changed. The change of slope is now from negative to positive. It's second order derivative, not first order derivative anymore. Okay, so there are like 3 to 4 steps to it. We'll just go from one by one, and those are like very briefly and elaborately explained in the slides. I'll just give you in like smaller points. So first thing that you need to know, you need to do is evaluate your function at zero. Then at the initial point that, okay, let's say extreme extrema, and then you have the extreme extrema on the positive side. So negative side and positive side. You need to evaluate your function at these 3 points. Now, doing so will tell you where is the starting whenever you want to plot a function, okay, and ending of your curve. Don't just like guess it and do it, but you just see it. Then you see the time, number of time your curve turns. Okay, so you saw in this particular case, you saw that it is turning 1, 2, and 3. It was turning this many times. So you see the number of points it is turning. Okay, your curve is turning. Now, where are the turning points? Right? What do you see is like catch for the points which are where are the turning points, and then you see what kind of turns. Now, in this case, we only have like two options for what kind of turns. And I suppose that you all know at this particular stage that that's something but positive, or either it can be a negative, right? So let's say if I give you an example, we'll just take an example of from what it was being taught in class. We'll take an example of x cube minus 3x. right? Your f of x is equals to this one term. So first you need to evaluate it at 0. At 0, you have 0, right? At negative infinity also, you have it as negative infinity. Whatever you do, it would be negative infinity. Again, if you input positive infinity, that would also be positive infinity. Now, you know that this one particular curve, even if you try and plot it, you see that it is at 0, it is 0, then it's negative infinity, it's positive infinity. It will go on both extreme ends till infinity, and at 0 only it's crossing at 0, so it is 0 at that point. Okay, sorry, the lights went off. 2 minutes. Okay, so we know this. Now next step what we have to do is like the time, number of time it turns. How do you get that number of time it turns? You do this df by dx. Okay, so the first derivative of the function. Now this was a step 1. Right, now a step 2. Now what would be a step 2? The derivative of the function. So what is the derivative here? Like think for a bit. So you take derivative, you do d by, always have an habit to write like this. It would be good for you whenever you are writing in exams or in even in your college exams and so. So like this. And then what it is, so this is 3x square minus you have 3. Now you have to evaluate it at 0, right? So this as 0, which determines that 3x square minus 3 is equals to 0. So you have x square minus 1 is equals to 0. So you see that x can get two positive values here, either plus 1 or minus 1. People always tend to forget this minus 1, but bear in mind whenever you have a square term on the other side, you'll eventually take a square root. That does mean that the other sign should be positive, but the term or the root that should be positive, but you always have a negative sign to it also. Of course, we know that it would be dumped on, but for this, it's like whenever you're solving and doing analysis like this, never ever skip on solutions that are critical roots for you. Okay. Now, next, where are the turning points? So for that, what do we do? We do double differentiation of it. Now, how do you do double differentiation? First term, what you differentiated, again, you differentiate it once more. So this one particular term that I have in this case, so I'll differentiate it again. So what it comes, this is 6x minus, I have 0 is equals to 0, right? This comes as this. So that's my dx square by this, which is nothing but I have 6x. Now for the 6x, I have this d square f by dx square as 6x. Now I'll evaluate it at this points. Okay, 2 points. 2 minutes. Yes. So now you evaluate it at x equals to plus 1 and you evaluate it at x equals to minus 1. So at plus 1 you have 6, minus 1 you have minus 6. So what do you know? For the one where it was positive is nothing but it's a minima for your case. That's how the definition stands on, and this is maximum. No, it's not all, it's not, I'm like telling you that, okay, this is how it is. It's like you see the slope also, huh? That you see that how it's the nature the change of the slope, change in the curvature is being changed over here. Now in this case, when it was positive, the double differentiation slope, you got this. Now when it's starting decreasing, you had a maxima at this point. Again, when it started increasing, you had a minima at this point. So that's how it comes from. Okay, so whenever your curve is nothing but increasing, your double differentiation is positive, it means that it had a minima somewhere. Also, when it's decreasing, that means it had a maxima after that one point, because always you are evaluating this limits at the critical points. And after this critical point only, this change in slope will occur. So that's how you see if you have a minima or maxima. Now you have this minima and maxima with you. Now you evaluate the function again. Okay, so now you know that at plus 1, you'll have a minima in your function, and minus 1, you have a maxima. So your step 4 is to evaluate the function at plus 1 and minus 1. right? Now you do 1 minus 3, that is minus 2, and you 1 plus 3, sorry, minus 1, and then you do plus 3, and that's positive 2. So you get these two values. So you have like the function of y, your y is equals to this two values that you got here, minus 2 and plus 2 when you had x equals to minus 1 and plus 1. So that's how then later you can plot that one particular derivative and see how it's being done. So this is how, like, if whenever you need to plot a curve, you need to remember these steps in mind. So where are the turning points? That just means that you need to find the df square by dx square, and then you evaluate it at those particular roots that you got, either the roots or the critical points. And once you have those, you evaluate it at positive and negative minima and maxima, the values that you just got the roots, and then against those roots, you evaluate your original function and you'll get the points that now you can easily plot the function that you have. Okay. Now, since you know this, I'll be skipping on the other two lectures. Those are like pretty much the same thing again and again. The first one is the first hand derivative. You'll do this one thing. The next one is the Taylor series. Both of the lectures that we have gone through. Okay. Now, for the last one, for L hospitals, I'll just show you how do you do that. We'll just Google up any source and see. L hospitals rule and an image that we'll take up from there. Okay. We won't go into basics of it. We'll just take an image which tells us pretty much everything. Mm. That's the definition of it. I just take this. Oh, wait, I wanted this one down. Says I cannot take it. Hmm. I want this. Can I copy it? Yeah, I can copy it. Okay, now we see. Uh-oh, it's not being pasted because it was. It's in dark mode. And this is also dark mode. We'll just take from somewhere else then. Let's say buy juice. It also has something like that. Yes, there we go. So here, you see that if limit one for one particular way, this isn't working on this one. We need a darker one. Can't see it though. Or it should be black. Oh yeah, okay. So we see that if a particular function when evaluated at the C, it tends to another function. That's nothing but this one. Okay, don't never mind. Just look at here that what this means is that x minus c tends to 0. Similarly, x minus c tends to 0. So if you have something where its limit is itself saying that x minus, okay, it's difficult to write using this pen. Okay. So if you have something as where you are evaluating the function as f of x minus c, which itself tends to 0, you'll have the function evaluated at f of 0, and that's 0. So in this case, we are just writing it. If this stands true, either it has 0 or plus minus infinity, then your g dash of x is not 0 for all x within this integers where this is not equals to c. And if you have like limit x tends to z, f dash of x by g dash of x exists, then you have this particular rule. So this is the final rule of what L Hospitals tells you, and that was like the limits, like how one each function should follow Oops, what happened? Okay, that didn't work on it. Okay. Let's just skip it. So this one particular one. So what happens in this particular case? So you see there are like these two different independent functions that you are trying to evaluate, and we see that if both of them independently approaches zero or infinity, but in other cases it's not directly equivalent to the say constant value that we're evaluating it at, then we see that whenever limit of x tends to c f of x by g of x, that will always be equals to limit x tends c f dash x by g dash of x. Okay, so that's a rule for L hospitals. Now since you know that, what happened? Okay, that's white in this case. We'll just look at few examples that are like just stated over here. So what now, basically simple thing. What you need to do is like you need to take derivatives in that case. So if you have a case like this, you have x squared minus x minus 6 by x minus 3 in this case, right? Now, what do? If you put in 3, let's see what you get. You have 3 minus 3, that's 0. So both that is 0. The upper one you see, 3 square is 9. 9 minus 3, 6. 6 minus 6 is 0. So both you have 0 by 0. That means that, okay, using this particular, we get a solution of 0 by 0. So you can solve it using L Hospital's rule. So how do you do that? You first take a derivative on the upper numerator that gives you like 2x minus 1, and then below you get a 1. So then you add x equals to 3 in this particular case. So you have 2 times 3 minus 1. You have 5 as an answer. So that's 5. So that's the required solution of how you evaluate this particular limit at. So that's how L hospitals work. We'll just look at another example. Let's say if you have limit x tends to 0 sine x by x. Now you add x equals to 0. You have sin x, a sin x of 0. What is a sine of 0? That's 0. And then x at 0, that's 0. So it follows the given function as 0 by 0. That's the basic definition. And that's what the condition we just saw now. If it's 0 by 0, then you can apply L Hospital's there. Now how you apply? Take differentiation of sin x, that's cos x, and then differentiate x, that's 1. So you have cos x at 0. What it is? That's 1. So you get 1 over here. Similarly, one another complex function in this case, you have like limit x tends to 0 e raised to x minus cos x by sine 2x. Okay. Now you see add 0. This is 0, 0, 1 minus 1 is 0. The below one is sine 2x, that's also 0. Now you apply the limit over here. How do you do so? E raised to x remains as e raised to x. So the differentiation of e raised to x is e raised to x itself, right? And then if it was some another like, let's say 2x or x squared, then we would have differentiated it again. Now since it's x, it would only be 1. So e raised to a x times 1. Okay, apply a chain rule there. Minus, you have differentiation of cos x is nothing but negative. Differentiation of cos x is, you have negative sin x. So in that case, it would have been a positive term there. Sine's differentiation is cos x, and cos x is negative sin x. But okay, let's see. This is sin x, and then you have sin 2x. So for sin 2x, differentiation of sin x is cos x. And then now you internally had this 2x inside. Now for 2x, you'll have to solve it as again differentiated. That's a chain rule. So you get differentiate 2x with respect to x. That's 2. So you get 2 cos 2x. Now you add 0, 1 minus 0. Okay, okay. Just see over here. Probably there's a printing mistake or something over here. The sign should have been positive here. But since sign 0 of 0, so they don't care in that case. E raised to x is nothing but 1. And then 2 cos 0 is nothing but 1. So you have nothing but 1 by 2. That's your answer. So that's how you can solve for L Hospital's rule. If there are no further questions, I'll like take a 2 minutes break and then we can go and solve the assignment for this week. That's it. I guess for this particular week, we didn't have much things because we have already solved in the last weeks. So if you have any further questions, you can always let me know. But for this week, it's done. And I'll just set up my tablet so that we can solve the assignment. Let's just see if it works this ways. I didn't get time to compile a PDF today, so I just took screenshots, but I don't think so that will work in this case. Let's see if it works. Well, something like this might work if I just copy to clipboard and then add it within this week 3 ka lecture ka note. Paste. Oh, great, that works. Similarly, for the second one, where's the gallery? Here. Again, we do the same thing. Copy to clipboard. Paste. Okay. Last third one. Oh, it's not coming. That's this one. Did I just copy the same one again? Let's see. Yeah, I did. This is 8, 4, 5, 6, 7, 8, and then we want 9, 10, 11. This is the same one. Oh, no, wait. You have a 9 here. Okay. You only have 9 questions here. Let's go right here. So that's been done. Okay. Yes. To write on top of it, I guess we need this black one. Yes, this black one. So I hope this is visible to all of you. Now you see over here. We need to calculate the derivative of at x equals to 3 for y is equals to x cube, taking this delta x as 0.1. So for this, like you'll have to solve it numerically, calculate the derivative for this, taking this. You'll have to solve it using the like a conventional definition, probably perhaps that they want here to like probably for you to get like see the ones, but it's not no longer needed nowadays, but it's fine if you just read it and go through it. So how we will do it is, okay, you have the first, let me just decrease the thickness for this pen. Mm. Never use this pen. That's why I always use that calligraphy one. Okay, so if you get this f dash of x, that is nothing but f of x plus your delta x, your conventional formula only, minus you have f of x and then you evaluate it at delta x. Okay, now you take y is equals to x cube here. So always what you do is now x plus delta x whole cube minus x plus delta x divided by delta x, right? And then don't remember that this all is nothing but within a limit where delta x tends to 0. Okay, that's how it's being done. Now what you have to do is like uh, okay, hmm we'll solve it. That's it. Hmm. Delta x is given as this. Now you just go through it. Okay. Simply, if you want to solve it, how else can we do it? Let's just think on it. Sorry. X cube. Did I write something extra here? Minus f of x. This should have been x cube, right? Yes. This is x cube. Again, you have an x here, so that will come as x cube. X cube you can take as constant. You eventually have a minus 1 sign outside. Okay. I'm just thinking if you don't need to elaborate it till all the way, or you will need to do that thing. Hmm. Wait. Okay. Let's just say either case you do. Okay. So let me just say. Okay. So if you have this term as a plus b whole cube, you get it as a cube plus you have b cube plus you have, I do remember it like this, 3a square b plus 3ab square. Okay, so you have things as this, and now you evaluate this entire term as x cube plus delta x cube. Sorry. Let's just write it x cube plus delta x cube plus 3x square delta x plus 3. x delta x square, and then you have minus x cube here, okay, by delta x, right? So this is what you have. And now you see that this x cube is cancelled, and then you have this delta x cube. So let's just take this delta x cube and delta x common. This delta x is eventually common for everything. So you do this as 1 plus, you have this as 3x square by delta x square, and then you have this as 3 x divided by delta x, right? Uh, Tell me in comments if this is clear or not. How do you do that? You take delta x cube out. So if you multiply this by 2 times of delta x, it would become delta x cube. So hence you divide it by delta x square. Similarly, in this the second case, if you have 2 times of delta x over here, now you want 3 times of delta x there to make it delta x cube. So hence you divide it by 1 time so that it becomes delta x cube. Okay. So after doing that, you get a square in this case, but I have like 3 terms in this case. Somehow the key doesn't have 3 terms. Okay, let's just see what answer can we get from here. Uh, mm, okay. So this makes it as delta x square, and then you have 1 plus 3 times 9, 3 square 9, then delta x square, so you have 0.1 square, and plus 3 3s are 9, divide by delta x, that's 0.1. Okay, so let's just evaluate this, and this is nothing but as 0.1 square. Okay, so evaluating it will get what? Let's see. So you have 0.1 square, that's 0.01. Okay, and then you have 1 plus 27 by 0.01 plus you have zero point 0.9, right? That you know. So you have 0.01 times 1 plus this is by this. So now if this goes up, it will be multiplication of it. Okay. So this becomes a big term right here. I don't know if that's correct or not. Now this 2700, you add zero point 0.9 to it and then you add 1 to it. Ah, okay. You get something as this. I guess these guys did miss a term when evaluating it. And then you multiplied it by 0.01. By looking at their answer key, I do think so they have done something like this. Because when we do this, we get an answer of 27.019. And the answer is 27.91. The other way around. I don't know. It's like they're trying to say that this one should not have been existed in case. So, like, just go through the calculations if I've done it correctly. Apart from that, how you need to solve is this one particular case. You do f of that particular function minus f of x, and then you just evaluate the limits out through here. So the formula for this is exactly like you take all 3 cubes in this case. Probably they did miss one term there, and hence missing that term is causing the value to be like this. But it's fine. We'll just look at it. Now, next, the second question. Take the function for classical measureless Benton kinetics is like V is equals to Vmx by Km plus x, where both of them are positive constants. So they are asking us whether this function has a minima, a maxima, a minimum maxima, or nothing. Okay, so what do we need to do for evaluating a minima or maxima for a function? We need to differentiate it. Simple as that. How do you differentiate it? Now, this is nothing but a product rule question. I'll just write next to it in this case. Okay, so let's see for question 2 here. So that's a product rule. V is equals to, you have Vmx divided by, you have something as Km plus x. Okay, so now Let's just do it as a quotient rule if it's fine with all of you, because I do want you guys to know that formula. Okay, so now keep your denominator constant, km plus x, differentiate to your numerator, that gives you vm. Then you have a minus sign, keep your numerator constant, and then differentiate your numerator. This goes 0 because that's a positive constant. This goes as 1. So again, you have 1. And then you have a square for this km plus x whole square. Right. Now, this term, you have one dependency. You have a constant here, Km, Vm, and then you have like Vmx, and then you have minus of Vmx. Right, that's nice. And then you have something as Km plus x, and then you have whole square. Now, this goes out. So you only have a constant on top, Km, Vm by Km plus x whole square. Okay, so that's our first derivative. And if we do evaluate the second derivative of it, it would nothing be like this 2 goes up and then you differentiate it. So that's as something as just keep the constant outside. You have 2 times km vm divide by you have km plus x. Because it was a minus sign there, so minus came back, minus 2 was up, so you have minus 2, minus 1, and minus 1, right? So minus 2, minus 1, that's 3, and we bring it back to denominator, so it becomes as positive 3. So you get something like this. Now, in this one case, you have an x which goes to power of 3, you have an x which goes to power of 2, you have an x which goes to power of 1, right? In that case, I like, without expanding it, you know that it is following a x cube relationship, right? Now, when it's following an x cube relationship, we just saw the formula for x cube relationship. So it will have an x cube term. It will also have something with this square, and this would be x, and then this square, and that would be a constant term, and then eventually would be this one particular constant terms cube, right? So now you have a combination of these three terms. Do you think you'll at least have a minima or maxima there? You won't have anything. That curve will have everything inside it, and that's nothing but would be something as a sigmoidal kind of curve. So you can go and try to plot this curve. So this particular curve does not have a maxima or a minima in this case. Okay. So the answer here is nothing. No, you don't have a maxima or a minima. Okay. Okay. Now next question. A patient had an initial temperature of 103 Fahrenheit. 1 hour after taking X milligram of a drug, the body temperature is given by this equation. How much drug does one should take that each one observes the maximum drop in temperature? So you want a maximum drop in temperature. Okay, so you want a maxima, you want to evaluate the maxima of it. So just take a derivative. So you have T is equals to 103 18 minus x divide by you have 200, right? You have things like this. Now you do dt by dx. You get this as 0. You get this as, okay, now you apply product rule over here. But before doing that, you take the constants outside. Now you do the product rule here. So for the first one, you have 2x and then you have 18 minus x as constant. And then you have plus, you have x square here, and then you have minus 1 in this case. Okay, so that will bring you to 1 minus 1 by 200. Then you have 18 2 is 36x minus you have 2x square minus you have x square. Okay, that brings us to pretty much a nice equation over here. So you have this minus 1 by 200. You have 36x minus 3x square. Now you do this dt by dx is equals to 0. So when you do that, you get 3x squared is equals to 36x. You can't directly subtract it, right? So you bring this to other side. How do you write it as? You take 3 and x common from here, you get an x outside, and then 2 here is equals to 0. So you get an x is equals to 0 and then 12. Because if you do directly there, you'll directly say that, okay, it's 12. You're canceling out x there, but you cannot. It is giving you one root there. That's nothing but 12. Okay. Now you want to evaluate dt square by dx square, and you want to see that what its value is. We want to see the maxima there. Okay, so we'll go on the other side. We'll just do on this one particular side expansion of this. Okay, so what do you want to do? We do d square, sorry, d square t by dx square. Okay, now you have this first term. Now you just take, so I'm doing for this one, okay, for this one that you see. I hope it's visible. Hmm. So you do it as 6x minus 36 is equals to 0. You do 6x, okay. So that comes as x minus 6 is equals to 0, and that gives you x equals to 6. So this is positive. So when you do dt square by dx square, you get a positive term. What that means that you have a minima apparently. Okay. At x equals to, so you get a critical root 6. You have a minima there. Now you evaluate your function at 12, the value that you get, that you got. Okay. Now at x equals to 12, because that's a critical root from here that you got, you want to evaluate this one function. 2 minutes. 30 minutes. क्या 10-15 मिनट ही बंद करना है टाइम हो गया 10-15 मिनट 10 मिनट के लिए Okay, so you have x equals to 12. Now what do you see over here? Oh, sorry. Today. Okay, so what do you do over here? At x equals to 12, you have 6 times 12 minus 36. So this is nothing but 672. 72 minus 36. How come these guys got it as... Okay, it's negative. Should one observe the maximum drop in temperature? So seeing it here also, what we are getting, let me cross check if I'm doing something wrong. So it's 6 times 12. Yeah, it's minus 36. So you eventually get 36 here, right? And at x equals to 12, this one particular term comes out to be positive. So that does mean that we have a minima and that's cross-checked by this term. But probably they did some sign mistakes here. We'll have to cross-check the answer. The answer is still 12 because that's what you get after differentiating the function at once. And this terms, after doing so, it should have a negative and negative if they want us to calculate the maxima in this particular case, that it observes a maximum drop in temperature. Um, for the maximum drop in temperature. Hmm. When would be a maximum drop in, so let's just say if you're just plotting it, and for this case it's constant, this is constant. Here it's decreasing. It's not plot for this particular equation, but we are just doing it randomly. In this it's increasing, this it's decreasing. In this case it's dropping, maximum drop. So my curve is negative. My change is negative. Here it's positive. And here I got a maxima when the curve is negative. This was a minima when I got a change as positive. Probably the wordings need to be changed in this case or something that they met, but okay, the answer is 12 in this case. Okay, so I'll just get back to you in next week. I'll just see what happened last week. But yeah, probably see the wordings much better. I'm not able to understand now how it is, how they're trying to say it here. Okay. Next question. We have how many maxima and minima are there for this one particular question. So now you know that what you want to do. You first do f dash of x. Then what you get? You get 4a. You get x cube minus you get 2bx. Right. Evaluate it at 0, you get x square as you get 2b by 4a. Okay, then you do the second derivative. So 4 is a 12a x square minus you do 2b. And now you evaluate it. So you take f dash of 0, so you get something as negative 2b because this term itself is 0, right? You take a second derivative for this term and then evaluate it at 0. So you get this one particular negative 2b term. Now you do this f dash of at this term that you got 2b by 4a. Now you had this at x square. The value is for x square. So you just do like one subtraction for it. This is x square. This is also x square. So you evaluate the function at that term. You see that what you get is 12a and then you have 2b. I'm rushing it because they want me to close this minus 2b. Okay, so in this one particular case you see that okay, this is also subtract minus this is 0. So in this case we have a maxima and a minima as well, both terms we have. Okay. Next question. Imagine a protein which is like a spring. At both initial points, it's 3 nanometer, the distance in between 2 points, in its equilibrium folded state. Any deviation would cause some energy and compute the energy at this. End-to-end distance is this. Knowing the mathematical expression using Taylor series expansion given as this. Limit the series up to second order, so third and higher order are 0 and assume the derivatives are unit 1. Okay, so this is nothing but Taylor series and we want the Taylor series for knowing the of the energy using for the energy using this particular series. So what that would be, that would be nothing but simply your e raised to x series, and how it would go is like x minus x naught plus you have half of, and assuming all other are nothing but 0, this. So you just take a derivative of it, input the values into it, you get an answer of something as 0.22. Yeah, there you go. You have an answer of 0.22 here. Okay, you just evaluate it at those terms. Then you have calculated the partial derivative of this. Now, what partial derivatives are, you don't derive it at that one particular point. So how you do it this, in this particular case, it would nothing be. Now, partial derivative, so in case of our original derivatives, anything, so here is a dx directly, this won't be evaluated, so it would be directly be 0, hence your answer is 2x here, right? Sorry. And then for this case also, you see that it is e raised to xy. So you do e raised to xy will also come in here, but it's again only derived with respect to x. You have x in this case, so you have your answer as e raised to 1. And this x is also 1, so your answer is e. Okay. And this we already did. So that would be nothing but cos x by 1. So that is cos 0 by 1. So that's 1. Okay. See if it's 0 by 0. If it's there only apply L hospitals there. Okay. This all we did, the last one. Okay. Now this is also, you do 1 minus 1 by 1 minus 1, that's 0 by 0. Now it's following. So you do 2x by 1. So this is 2. So your answer is 2. Okay, I hope this all are clear to you. If you have any further doubts, please feel free to reach out to me via the YouTube comment section, or either we will meet next week. I know that logs is still pending. I did prepare. I'll add it into the lecture slides, the folder where you find all the content. You can go through it. If you have any questions, let me know next time. I have a written lecture, written notes for it also. So I wanted to share today, but I cannot because of the space restrictions. So sorry for today, and thank you. Let me know if you have any questions further. Okay, see you next week.